Okay, this video is being created for the Algebra II Honors Plus classes for those students who may like to have a little bit of a review on their factoring skills. Maybe you feel like you just didn't practice this enough in middle school. Maybe you feel like your teacher in middle school did not emphasize the factoring techniques as much, or you just have forgotten some of them. So this handout is for students to review independently and to give you a little bit more help if you would like some extra knowledge about factoring. Okay, so if you do need extra help beyond this, kind of after you work through this video, I would visit the Math Tutoring Lab. The tutoring lab is in room 202, and it's open on Monday, Tuesdays, and Thursdays from 3:30 to 5, and you can just drop in. You can take this packet. Any type of problems that we're working on in class, you can head that way and get a little extra help. All right, so we've discussed polynomials in class, and we understand what a polynomial is. That was in section 0.3. We basically talked about the operations on polynomials, that we can add two polynomials together, and polynomials are closed over the operation of addition. If you add two polynomials and you get a polynomial. If you subtract two polynomials, you get a polynomial, and we also worked on the product of two polynomials, which is also a polynomial. So polynomials are closed under the operations of addition, subtraction, and multiplication. And then the idea here is that when we are multiplying out polynomials, there will be times where we would like to work backwards, that we would like to quote-unquote unmultiply a polynomial. And that's what factoring basically is. It's this idea that we want to write it in its factored form. If we relate this to the sets of numbers that we were talking about before, when you write a number in its prime factorization, you are putting it in its factored form. You are looking at the factors, okay? So we want to unmultiply, okay? Defining what a factor is, a polynomial, we're going to say, evenly divides another polynomial, is a factor of that polynomial. What we mean is that we must be able to write this polynomial as a product of 2x plus 1 and some other polynomial factor that will give us the end result. We're going to unmultiply. Now you're typically used to, you can use the guess and check, but this one's pretty easy. If you already know 1, you should be able to come up with the alternative factor. We know that the first two terms have to multiply to give me 4x squared. So you're pretty much going, hey, the first term in the other factor is 2x. And we know that the last two terms in the factors have to multiply to give us the constant term in the polynomial. And since that's a 1, your only choice is that you need to have a 1 over here. And then we pay attention to the inner and the outer. The combination, the sum of the inner product and the outer product has to add to the middle term. And so the only way that would happen is if we put a plus here, because then we would have 2x plus 2x equals that. So 2x plus 1 is a factor. It divides into it evenly because we know that if we were to divide it out, we got another polynomial. All right. X plus 7 and x minus 7 are factors of x squared minus 49. Okay. We learned in our reading in section 0.3 the difference of perfect squares. So it factors into our sum and difference of linear terms, linear binomials. And so the idea is that you should be able to have this skill of figuring out how to unmultiply a polynomial. We are going to consider a polynomial prime, which basically means not factorable over the reals, if it has exactly two factors, only one and itself. There is no other polynomial that divides into it evenly other than itself and 1. We call polynomials that are prime irreducible over reals. Now I'm stressing that because right now we're living in real world, okay? So all of these factors that we're looking at, this is considered a linear factor, and it is a polynomial where we're only considering that it's defined over reals. We are living in real world. We're not living in complex world, which we will talk about at the end of this chapter. Okay. X plus 5 is prime. It's linear. There's no way to reduce it. X squared plus 4 is prime because there are no real factors of x squared plus 4. Okay? Don't get confused and try to do a plus and a minus like we did up here. You're required to have the minus here in order to get it to factor into this fashion. Your x squared plus 4x plus 1 is prime. And let's talk about why that is. How did I tell that something is prime? Okay? We could start with the guess and check method, okay, kind of that I used above. We know that the first two terms in each factor would have to multiply to give me x squared. And I know that there are two factors, if they exist, because it's an x squared, okay? Because polynomials, the degree of your polynomial either has to be a constant, which would make the degree 0, 1, 2, 3, and so on. Okay, so we're talking about our whole numbers. So when I have x squared, if I have x squared, I know that I can have basically two factors if it will factor into two separate polynomials and two linear factors. I know that if it's a cubic, I would have three factors, that if it factored, I could get three of them, and so on, and so on, and so on. So the idea is that we want to figure out what's going on. We know we have two if they exist. We know that the first times the first have to give you the first term in the trinomial. So there's my x. You only had one option. I know that the last times the last have to give me the constant term. So 1 and 1. Those are your only options. Now, from here, you know that your middle terms have to add up in some fashion to 4x. And you're going to put pluses or minuses here to make that happen. Well, if I do plus and plus, I end up with x plus x. That's only 2x. If I do a minus and a plus, I'm going to end up with them canceling out and not having a middle term over here. And if I did minus and minus, I would end up with a total of minus 2x. And so that's not going to give me the 4x. So there is no combination of the factors of the last times the last. There's no combination of this inner and outer that's going to give me 4x. Okay, so that's the tedious method. You kind of have to check. Now this one was easy because there weren't very many factors of these two that are going to add up to the middle term. You only had x and 1, so it made it easy to kind of guess and check. An easier way is to utilize something from the quadratic formula. This only really works for the quadratics. And under the radical, you had b squared minus 4ac. Okay? If b squared minus 4ac, where you have ax squared plus bx plus c, thinking about this as your trinomial here for your quadratic, that if I were to plug in the coefficient of the x term for b, the coefficient of the x squared term for a, and the constant term for c, if this equals a positive perfect square, okay, if that equals a positive perfect square, then we know that this factors. If it doesn't equal a positive perfect square, then it doesn't factor. Okay, so if, and this has a name, it's called the discriminant. If the discriminant from the quadratic formula is a positive perfect square, then the quadratic factors. All right. We also want to take this idea of looking at the greatest common factor, that we want to be able to pull out a GCF, and that's kind of our first step in factoring, if they do have a GCF. Now, in all of these examples, there is no common factor to all three terms or two terms in the polynomial, so there was no GCF. Okay, so down here, if I had these as two terms in my polynomial, I look for first the greatest common factor of the numbers, which is 5. Okay, the factor that divides into both. And then I look for the factor that divides into both x cubed and x to the 4th. And you always go with the x to the smallest power. X is a factor of both of these terms because there's an x and there's an x. And we want to find the greatest common factor would be the smallest power, because the smallest power would go into x cubed, and the smallest power would also go into x to the 4th, that it would divide into it evenly. So our GCF would be 5x cubed. If I was thinking of this as a factoring problem, where maybe, for example, we had 25x cubed plus 5x to the fourth, and I wanted to factor this, I would identify my GCF to pull out. And factoring is unmultiplying, which is kind of like dividing it out. If I were to divide 25 by 5, I get 5. And x cubed divided by x cubed is really 1, so I don't need to write it. Plus 5 divided by 5 gives me 1. And then x to the fourth divided by x cubed is x. That's what you have left. You can check that you've done this correctly when you pull it out, because if you were to distribute, to actually multiply it through, you should get this answer. Factoring is unmultiplying. So you pull it out to unmultiply it, you can put it back in to check your answer. All right, if I look at number 2, okay, your GCF here, if you have a negative and a positive, you pretty much, there's kind of a generic thing with the negatives. Sometimes you pull a negative, sometimes you don't. When you look at the powers, the degree of the polynomials, if the negative is with the higher degree, we typically try to pull it out. If it's not, if it's on both, we definitely pull it out. But if it's on the smaller powered x term, then we're going to leave it in. Okay, so I'm going to pull out, I'm going to say my GCF is 3, because 3 divides into 3, 3 divides into 27. And then my smallest power of x would be 1. So 3x is my GCF. If I saw this as a polynomial problem, where I have 27x to the 8th minus 3x, I would factor that by saying, hey, I have a common factor. I can pull a 3 out, and I can pull out an x. We could also say this as we can divide out a 3, and we can divide out an x. And when I do that, what's left, the remaining factor, is going to be a 9, 27 divided by 3, and then x to the 8th divided by x, x to the 7th, minus 1. Okay, so we're pulling out a GCF. All right, and then to completely factor a polynomial, we want to get it to the product of prime polynomials. We want to get it to the point where it doesn't factor anymore. And so like in this example, 9x to the 7th minus 1 is not something that we're going to be able to factor, quote unquote, nicely on this. We'll talk about what will happen with this later when we get into chapters 4 and 5 about how to treat a higher degree polynomial like this. But right now we're just trying to get it nicely factored, and this would probably be where you would stop. Okay? Now typically, why do we try to factor? The main reason that we are factoring polynomials is because they are going to give us information about when we're trying to solve the equation, when we take this polynomial in x, that's what this means, and we set it equal to 0, there will be times where this is going to be important. It's going to help us find x-intercepts on graphs. It may find solutions to equations. And so the idea is that once I get it factored, and I have factor 1 times factor 2 equals 0, by the zero product property, then either a equals 0 or b equals 0. So that's kind of the point. That's what we're trying to have a perspective on. We also factor polynomials. I didn't say it here, but we also factor polynomials because sometimes we want to be able to compare polynomials, or maybe we have a fraction where you have a polynomial in the top and a polynomial in the bottom, and you're looking for common factors that you can divide out to simplify. So these are all things about why factoring is important. All right, so let's say we want to factor something like this. Typically, you're going to work with quadratics a lot right now because you don't really know a lot about higher degree functions, although some of them may not quite be quadratic. We're going to look at some functions that don't appear to be quadratic, but will be quadratic in form. And we're going to look at things that have a greatest common factor. Okay? If you see things like x squared plus 6x plus 9, I am expecting you to recognize that this is the product of a binomial sum. That this is a special factoring form from section 0.3 you're just supposed to memorize. And so you would recognize that the a is the x, the b is the 3, and the 2ab, 2 times 3 times x, is going to give me the 6x, and that you should be able to factor it. Here is the difference of perfect squares. This is the perfect square of 2x. 81 is the perfect square of 9. So you should be able to recognize that you have this difference of perfect squares and immediately factor it to your a plus b and then your a minus b, special factoring forms. Your x squared plus 36, you need to recognize that's not a special factoring form because that is the sum of a perfect square, and that is considered to be prime over reals. So that does not factor any farther. Now, taking a look, the first step in factoring, and I can't stress this enough, your first step in factoring is to always do GCF. Make the problem, simplify early, simplify often. So it's easier to pull out common factors and then try to factor what's left than to try to factor a really complicated one. So like in this one, it's a quadratic. Don't start doing guess and check on this. Recognize that and check to see if you have a common factor. 3 divides into 3, 3 divides into 30, 3 divides into 48. So I'm going to pull the 3 out. It's only a number, which is fine, but it's going to make the problem easier to work with. Simplify early, simplify often. So we pull out my GCF. 30 divided by 3 is 10. 48 divided by 3. 3 goes into 48 once, so plus 1, carry your 1. 3 goes into 18, 16 times. Okay, that's only the first step though. Remember that what you want to do from this point, okay, so that if I just said factor the GCF out, you're done. But really we want to factor completely, so now we want to see if this factors. Now this is a nice one because your coefficient here is 1. If it factored, it would have to have an x and an x. So now we're looking for factors of 16 that will add and give us 10x. So our factors of 16, 1 and 16, not going to work. 2 and 8, 2 and 8 seem to be working. And if I had a plus and a plus, my inner and my outer would add to the middle term. So then I can get to my completely factored. It is easier to simplify early and often. Pull your GCF out first. All right, over here, I notice that there's no number that they have in common, but they all have an x. Each term has an x, so x would be considered a common factor. And I pull the x with the smallest power because it has to divide into it. I know that x divides into x cubed, x is going to divide into x squared, and x is going to divide into x. If this had been a square here, I would have taken a square out. You take the smallest power that you see because you want to make sure it divides into all the terms. When I divide the x out of x cubed, I have x squared because I subtract my exponents when I divide. Then I have my minus 3. I pulled the x out, I pulled 1 away, so I divide by x. I subtract my exponents, minus 3x, and plus 24 because I divided out. Then I can take a look at this and see if this factors. So I pull the GCF out first, simplify early, simplify often, and then we go to this quadratic and say, does that factor? Again, your coefficient, the leading coefficient is 1, so we know it's x and x. 24, we need factors of 24 that are going to add to negative 3. So let's go 1 and 24, not going to work. You have 2 and 12, not going to work. You have 3 and 8 is 24. That one's not going to work. You have 4 and 6. That's not going to work. Okay, and once I get there, I'm pretty much done because I've hit all of them. All right, so let's back up. Let's check that discriminant. Let's go ahead and mark that off. We don't think this factors. We think we're done right now. These are two prime factors. Let's check the discriminant just to see how that works. My A is 1, B is negative 3, C is 24. So when I do the discriminant, and the discriminant doesn't, even though it's under the radical, you just really need the b squared minus 4ac. And then I plug in what I have. B is negative 3. Pay attention to parentheses, it matters, because I'm squaring the whole b. Minus 4 times 1 times 24. And just by looking at this, I don't even have to really calculate it. even though this is, what, 80, 96? This right here is going to be a negative number. Remember, the rule was, in order for it to factor over the reals, it had to be a positive perfect square. So I'm done. It does not factor. This factor is prime. I don't say that what I started with is prime, because it did factor into two polynomials. Now I have two polynomials that are irreducible, do not factor any farther. Okay? All right, let's take a look at the next example. I'm looking for a number that divides. I always do the numbers first. 21, 28, 7. Okay, they're all divisible by 7, so we're going to pull out a GCF of 7. And then every term has an x. And the smallest power that's there between 4, 3, and 2 is 2. So I'm going to pull out an x squared. 21 divided by 7 is 3. X to the fourth divided by x squared, 4 minus 2 is x squared. 28 divided by 7 is 4. X cubed divided by x squared, 3 minus 2, 1. And then x squared, or 7 divided by 7 is just 1, so I don't need to write it. And then x squared divided by x squared is 1. So 1 times 1 is 1. Now we check. This one's prime. We're done with that one. Now we check this quadratic. Your choices here, if it factored, okay, 7x squared, 3x, and x. Your only choices here are 1 and 1. And is there a way to get a minus 4? I have an x and a 3x. You're like, yeah, if I put a minus and a minus. So we can factor that. Just to verify to you that the whole discriminant thing works, your discriminant for this example, when you're doing 3, 4, negative 4, and 1, a is 3, b is negative 4, c is 1. So your discriminant, b squared minus 4ac, would be 16 minus 4 times 3 times 1. 16 minus 12 is 4, positive perfect square. So if you're stuck and you're trying to figure out whether it factors or not, go check your discriminant, see if it does. If you get a positive perfect square, go back to your guess and check and try to figure out where the factors are. Okay. All right, now, so completely factoring the polynomials, this first thing, you'll notice that in all the examples I've done so far, when the coefficient of the squared term is 1, or only has 2 factors, I pretty much only do guess and check. That's the technique. I go, what are the factors of x? X and x. What are the factors of 10 that add? What are the factors of 10 that make the inner and the outer add to 7? And then so you just, there you go, very quickly. You can always check your answer, because once I've unmultiplied it, I can multiply it back out and see that I get the same answer. Okay? So I'm going to leave these for you to practice. I'm going to basically count to 5 here, or 10, and I'm going to then pause the video. So I want you to try these on your own, sitting at home. Pause the video, and then when you have them finished, hit play again, and then check your answers. All right, so hit pause. Okay, so here are your answers. So go ahead and check. If you missed several of these, go to tutoring. You're going to need help with this. One comment that I will make, let's come down here to F. Did you remember to do your GCF first? Okay. It is possible that you may have factored it. It's not impossible to factor without taking out the GCF. It is just longer and less efficient. If you had tried to do this, or maybe your answer might be something along the lines of 3x plus 3 times x plus 4. This is not considered factored completely because this factor still has a GCF to take out. Okay, and plus it's a harder problem to do because you're trying to guess and check because there are many factors of 12 as well as the factors of 3. Always do GCF first. It's going to make your life easier. Okay? Now, when you have the second term, notice that in all of these, the guess and check was fairly easy. They were always x plus in this. All right, that makes it a little easier. When we have a minus as this term, we just need to make sure that when we factor, we're still looking for x and x gives you x squared, 1 and 4 or 2 and 2, and you need the inner and the outer to add to -5. And the only time that you can get, because this is a +4, you've got to have both negative or both positive, and then when that's negative, you need them both negative. So you're just practicing to recognize when do you need both factors that have subtraction in them. Right? So again, your turn to practice. I want you to pause the video and then come back when you're ready to check your answers. All right, check your answers. A couple of comments. Don't be tempted, like here, you get into the, hey, I have 12 and 1, and if you have a -12 and a +1, you get -11. But the problem is this. As soon as you see this plus, you know they have to both be negative. So when I do my factors, notice I'm listing them so they're both negative, and I need these two things to add to -11, which they don't. I could check my discriminant and see that I get 73, which is positive, but not a perfect square. This one was prime. Right? And so the idea is you should get fairly straightforward. These are coefficient of 1. Maybe this one was a little long. You had to come up with the factors. You had to recognize the factoring form, but you'll get there. All right? Now let's take a look at the next case. Now I'm going to have the third term being negative. Okay? So you pretty much know that when you are doing your factors, you have to have one positive and one negative. So I need the sum of these to still end up being 3x, and because this is positive, I need the larger one positive, okay, because it ends up being a positive number when I add. So that should kind of keep you straight on this. So again, I'm going to let you do the practice. I'm going to hit pause, do your work, you hit pause, come back when you're ready to check your answers. All right, take a moment, check your answers. Again, if you're struggling with this, please go to the tutoring lab and get a little extra help. All right, now let's look at some examples where we're factoring trinomials whose leading coefficient is different from 1, okay? And there's 3 different methods. There's factoring by grouping. So sometimes what you'll do is you'll take kind of your middle term and you'll split it up into some way that is going to help us figure out what the grouping is going to be. So we take our lead coefficient times the constant term. That gives us the -72x squared. We are going to look for factors of this number that add up to the x term. This is where we're trying to split the term into 2 so that we can do factoring by grouping. And we realize that if I have -9x and 8x, that adds to -x. And this times this gives me -72x squared. We're going to rewrite the middle term. We're going to change it from -x and replace it with the 2 terms. Right? So remember, this is -x. Then you have it where you have them grouped. So we are then going to factor by grouping, which is, now we look at the first 2 terms and say they have a common factor of a 3 and an x. We pull that out. We get 2x minus 3. We do the same thing on this side. Don't forget to bring your plus down. We pull out the 4. You're left with 2x minus 3. And you will know that you are in a good factoring by grouping situation because these 2 factors in the terms will match. You have a GCF that may be a little bit more complicated, but I have a GCF of the first term and the second term both have this 2x minus 3. So we pull that out. When we divide by 2x minus 3, we're left with 3x in the first term, and we're left with 4 in the second term. Okay? Let's factor this by grouping. Go through the same process. We multiply the first times the last. We're going to get 30x squared. All right, so now we're looking for factors of 30x squared that sum to 17. Okay, so start listing them out. You have x and 30x. You have 2x and 15x. And as soon as I hit that, I should be like, hey, look, 2x and 15x. So we're going to use those. We rewrite it. 3x squared. We split the 17x, and it doesn't really matter which order you go with the bigger one first, plus 10. So now I have the first two grouped together. I pull out a GCF, pull out the 3 and an x. You're left with x plus 5. You pull out your 2 and your 10, or your 2, because it divides into both. You're left with x plus 5. We have achieved success because we have the same factor in each term. So I'm going to pull that out as a GCF. And when I divide that out, the first term, you take away the x plus 5, you have a 3x left. You divide out the x plus 5, you have a 2 left. And so we have this factored. Factoring by grouping. We can use a table to factor by grouping. This is kind of this idea of what we call this the box method. Just helps you organize the factoring by grouping. Okay, you're going to write the first term and the last term. First, last, and then you multiply, which is what we did in the grouping thing. We get 6x squared. You still do the factors of 6x squared, and we're looking for ones that sum to 7x. So we start making our list. We have x and 6x, and right there, hit it, jackpot, right at the beginning. So x and 6x add to 7x. These are placed in your table in the other diagonal. Does not matter what order you put them in, okay? So these are your factors that add up to my 7x, my middle term. Now, what the table does is all it's doing is grouping them together. We're going to consider this to be a group. Pull the GCF of this row out. They are both divisible by x. Okay? You pull the GCF out of this row. They're both divisible by 3. Remember, you have two factors, so now I'm going to do the columns. The GCF of this column is 2x. The GCF of this column, well, they don't really have anything in column. There's no number, and there's no x to a power in both, so we just put a 1. And what that tells us is that this factors to one factor is this row, 2x plus 1. The other factor is the x plus 3. It is essentially factoring by grouping, but using a box to organize it. Okay. So I could have written it down here. My final answer, 2x plus 1, x plus 3. All right, let's take a look at this one. So I take my first and my last. Don't forget to bring the negative with you. I multiply. You end up with negative 72x squared. So I need the factors of negative 72x squared that sum to the middle term, negative x. Okay, so by guess and check, you can just start listing. Obviously, 1 and 72 is not going to work. So I start going things and realize that, yes, that 9x and 8x, and the bigger one would have to be negative. So I put them in this location. And you're going to do the same thing. There's going to be one caveat here, though. Okay, you're going to pull out the GCF of this row. They're both divisible by 2 and x. Now here, the rule is, if the first term is negative, pull a negative out. Okay. And then we go, is there anything else they have in common? They're both divisible by 3. Okay. Now coming down here, it doesn't matter that this is negative when I do this column because the first one is positive. So I'm only going to pull out the 3 and an x here. And then I'm going to pull out, again, I'm not worried about this one's negative, but the first one's not. So I'm going to pull out just the 4. So what that tells me is that my 6x squared minus x minus 12 is equal to 2x minus 3, 3x plus 4. Now you can double check this and see that if you multiply it back out, you get that. All right, so now when I have something like this, if I'm going to use the box method, a lot of times I just come in and I just draw myself a box. 3x squared, 10. 30x squared. I start looking for the two factors that add to 17. Okay. So we have 2x and 15x. We just did this by grouping on the previous page. We know the answer. I'm just showing you how it works with the box method. I put my 2x and my 15x, and then I go for my GCF of this row, GCF here, GCF there, and then GCF there, and we get that it factors 3x plus 2x plus 5. It takes a little of the guess and check out and makes it a little bit more organized. All right, then this whole educated guess and check is this idea that you're trying to play around with and figure out how this multiplication works. We know that the first times the first, 2x squared, last times the last, plus 3 gives me the leading term and the constant term. And then we know that the middle terms added together, the inner product and the outer product, are going to give me the middle term. I'm going to write them in 2 steps and then I'll put them together. So we have plus 1 times x plus 3 times 2x, 6x, okay, working backwards. So the factored form of a polynomial, this, if I were to multiply it back out, the polynomial we get is 2x squared plus 7x plus 3, right? What 2 terms of the factored form multiply to 2x squared? You're like, hey, 2x and x. What 2 terms the factored form multiply to 3? 3 and 1. What do I do to get the 7x? How do I relate the 7x into it? Well, I'm basically taking these 2 multiplied times these 2 multiplied, adding them together, 2x times 3 plus x times 1, and seeing if I get 7x. So it's basically doing factoring by grouping, but it's kind of a guess and check, right? So you first think of how the first term was created. You may have more than one option. In this case, I only have 2x and x. Then you look at how the last term was created, figure out what goes in those locations, and then you look at the plus and plus to recognize that you would have 2 positives, and then make sure you add to the middle term, okay? And you can kind of, when you have 3 and 1 and 1 and 3, your choices are it's either 3 and 1 or 1 and 3, and you do the one that works, the one that inner product, outer product adds to the correct middle term. Right? So my guess and check method, 3x squared, 3x and x. All right? Now look at my 4. My factors of negative 4 are either going to be negative 4 and 1 or negative 2 and 2. So now you're trying to figure out which of these, when I put them in here, are going to give me inner and outers that work out. Okay, this is a little tedious. Guess and check is. You guess, you check, you guess, you check. Let's guess that it's minus 4 plus 1. See if we get lucky. Check your inner and outer product. You're going to get minus 4x plus 3x. Guess what? That does not equal 11. Wrong. Try again. 3x and x. I could try plus 1 and minus 4. Check your inner and your outer. I get x, and then minus 12x, and then we say, yay, because that equals negative 11x. So this is my answer. I list my factors, I guess what order they go in, and then I check. Doesn't work, cross it off. Say, all right, that guess and check failed. Go to the next one. Flip them around. If this hadn't worked, I would have gone to negative 2, 2. Check the order. So you have up to 4 in this time to check. Guess and check's not the best method, but if you're fast enough, you should be able to see it. All right, let's do this by 2 methods. I'm going to do the box method first. In the box method, draw your box. 6x squared, negative 20, multiply negative 120x squared. I am looking for factors of negative 120x squared that add to 7x. So I immediately know, because it's a minus and a plus, one's negative, one's positive. And I'm looking for factors of basically 120 that add to 7. So if we need to, we can come over on the side and be going like 120. We could do 1 and 120. You're obviously going to skip some of these. 2 and 60, 3 and 40. You can do 4 and 30. You need to start getting closer. 5 goes into this 22 times. 6 goes into this 20 times. We're getting closer. 7 doesn't go into it. Does 8 go into it? I believe so. 8 goes into 12 once. 4, 15. Oh, wait, 8 and 15. Depending on how good you are at seeing the factors of a number, okay, it'll help you get there. Now, 8 and 15. Now, remember, we're subtracting. 15 minus 8, yeah. And I want to get positive 7, so I'm going to make the 15x minus 8x. 15 minus 8 is 7. List them over here. Then you look for your GCF, 3x. GCF, remember, first one's negative. Pull it out. So we have a negative, a 4. Over here, first one's positive, so I only pull the positive. I need a 2 and an x. And here, they're both divisible by 5. So we believe that this is going to factor 6x squared plus 7x minus 20 factors to 2x plus 5, 3x minus 4. And you can double check by multiplying it out. All right, method 2, let's do the guess and check. We've done a lot of work on this. Okay, now the guess and check method, this is why it's kind of going to fail. You're like, okay, I need the factors that will multiply to 6x squared. Your choices are going to be 6x and x, or 3x and 2x. I have two options, so I got to play around with both of these when I do my guess and check. We might get lucky and get it early. Now I need the factors of 20. Factors of 20 are 20 and 1, 4 and 5, 2 and 10, and that's it. Okay? We know based on the signs that we have a plus and a minus, that it's going to have one positive and one negative. It could be a plus minus, or it could be a minus plus. I'll do the same thing down here. Plus minus, or minus plus. I don't know which one it is, but I know that they're different. And then I start checking my choices here. Now remember, we're doing the inner plus the outer have to go to 7x. Now we've already done some work here, and hopefully when you look at this, you're like, okay, what am I going to end up? I definitely know, okay, that I am not going to put a 4 here, because it would have had to have a GCF if I did that. So I know 4 is not going to go here. So let's try the 5 and the 4. If I test this, I get 5x minus 24. That's not going to give me 7. So you go, yep, that guess and check failed. All right. I know it can't be 4 and 5 because of the GCF thing. So then I go, all right, what about 2 and 10? Well, that's not going to work, GCF. I could do 1 and 20. And hopefully you'll see fairly quickly you're going to have 120 minus 1. That's not going to work. Okay? So that guess and check failed. Come down here. So let's go back. Now we're going to do, odds are, reason it out. Probably going to be the 4 and the 5. Try the 4 and the 5 in this location. Check. 8x minus 15. That's minus 7. I'm like, okay, I'm close. I have the opposite. So maybe what I need to do is do 5 and 4. Minus 10x, and then plus 12. Okay, that doesn't work either. Now what do I do? Okay, maybe instead of switching both the sign and this, see, guess and check. You're like, all right, let's try the 3x. Let's go back to the plus, and let's switch just the signs. Okay, let's leave it as 4 and 5. But instead of doing the plus and the minus, like I did in the first one, see, this like guess and check is not the best method. You got to get a better method. Change that to a minus, change that to a plus. A lot of times you can reason out simple ones. But sometimes when they're harder, this is tedious to go through. Guess, check, doesn't work. Guess, check again, doesn't work. Guess, check again. Minus 8, plus 15, there I've got my 7. Okay? So that would be the answer, same answer that I got over here. Notice that When I have lots of factors of the leading term and lots of factors of the constant term, the box method is going to be your best bet. All right, so I am going to leave the more practice on this for you to do on your own, and I'll put the key to this up in its learning so you can check it. Let's skip over to the next page. Recognizing special factoring forms, definitely a skill. This one you have to recognize is prime, sum of perfect squares, no GCF. Over here I have, it is a subtraction even though it's not written in standard form. You might want to make this 9y squared minus 49. Okay. It doesn't bother me that this is the 64 and there's a variable here. All I care about is I have a difference of perfect squares. Difference of perfect squares, difference of perfect squares. Your job is to be able to recognize what this is the perfect square of. This is the perfect square of 2x. So I go 2x and 2x. I do a plus and a minus, and I say, what's this the perfect square of? 5. There you go, factor. Come over to here. Same thing. I have a perfect square minus a perfect square. Even though it's a decimal, that's still a perfect square. So I make my two factors. I go, what's 64 is the perfect square of 8 and 8. I do a plus and a minus. Now you might have to figure out the decimal. Take a moment, figure out what 1.44 is the square of. All right, 1.44 is the square of 1.2, so it would be 1.2a, 1.2a. Right. Let's come over here to this one. We recognize we have difference of perfect squares. 1/4 y squared is the square of 1/2 y plus minus x and x. Okay. Now over here, before I start this one, you'll be like, this is not the difference of perfect squares. Yes, but it will be if I remember to take out my GCF, x squared minus 81, and then I factor x plus 9, x minus 9. Okay? So recognizing difference of perfect squares. All right? The missing term to make this a perfect square trinomial, this is to make you help recognize when you have it. That this is the square of x, this is the square of 7, and 2 times 7 times x would be 14x. 2 times 7 times x. I'm doing this part of the problem. Okay? Now over here, I'm missing the last term. But I notice that this is 2y squared. So I need to figure out what constant would I add in here, let's just call it c for a moment, so that I get the middle term of 2 times 2y times this constant squared. All right? So now look, middle term. 2 times 2y, that's 4y times this constant. This constant must be 9, so 9 squared must be 81. Okay, figuring out what you're going to add. What does this first term have to be? Let's take a look at this. 9 is 3 squared. 18 is minus 2 times 3 times, what do I have left? This would be minus 6, so I end up with 3x. So 3x must be what goes over here, squared, so you end up with 9x squared. So being able to see and recognize your perfect square trinomials. All right, so let's factor. You look at this and you say, well, that's the square of 3z. So we're trying to see if we recognize this as a perfect square trinomial. The square of this, 2. And then I check is minus 2 times 3z times 2 equal to minus 12. The answer is yes. So we know that we have a perfect square trinomial, that it factors into the difference of two terms that are squared. This is 3z minus 2 squared. And so hopefully you start recognizing it. You had an x, a 6. Is this 2 times 6 times that? No. This is not a perfect square trinomial. Not perfect square trinomial. So I know it doesn't factor into this fashion, not with a plus in it. So then I go, are there any other methods? So let's try. Let's do guess and check. X and X. 36, 1 and 36, 2 and 12, no, 2 and, how many times is 2? 2 and 18, is that right? 2 goes into 36, 1, yeah, 2 and 18. 3 goes in 12. 4 goes in 9. 5, nope, done. Are we done? 6 and 6. Let's check our discriminant. B squared minus 4AC before I say I'm prime. B squared is 36 minus 4 times 1 times 36. I don't need to do any work. I see that's negative. So this is prime. Okay. Let's take a look at this one. We have 4x. We have a 1. 2 times 4 times 1, 8. Yep, I think this one's going to work. So 4x minus 1 squared. Okay, over here, we check. We have our y and 0.03, or let's check. It's really 0.3 squared would be 0.09. So this is 0.3 squared. This is y squared. Is the middle term 2 times 0.3 times y? Why, yes, it is. So this would be y minus 0.3 squared. All right, check down here. Before you start, don't forget, simplify early and often. Take out your GCF. Then see if what we have factors. This is x, this is 1, this is not a special factoring form. Okay, does it factor? Probably not. We could check our discriminant, b squared minus 4ac, which would give us 16 minus 4 times 1, which is 12. Positive, but not a perfect square. So the only thing we can do is get it to here, and then we're done. We just pulled the GCF out, and that was it. Okay, over here, don't let fractions bother you. We have an x, we have a 1/3. Is this minus 2 times 1/3 times x? Yes, it is. This is a perfect square trinomial. X minus 1/3 squared. And then that's it. So that's your quick review of your factoring skills from Algebra 1. Please go to the tutoring lab if you need more help.